Learning in problem with high-dimensional input spaces requires to consider complex models, which need many samples to be trained. This is called the curse of dimensionality. Dimensionality reduction aims at representing our dataset in lower dimensions, while maintaining most of the information that is contained in our dataset. Working on a compressed representation requires less samples, but compressing too much can be harmful, as we risk losing relevant information. We need to manage this trade-off in relation to the number of examples available in our dataset. Let's consider, for instance, a dataset of face images. Each example is a face, represented by an image containing millions of pixels. Working in such a high-dimensional space consumes a large amount of memory and computational power, and most of all, it is useless. What is the probability of generating the image of a face by picking an image at random? Almost zero. This is a symptom that the representation that we are using is not effective for representing the information contained in our dataset. We can leverage the structure in our data to build a new and more compact representation on which it will be easier to solve new learning tasks. One of the most popular dimensionality reduction techniques is principal component analysis, or PCA. Starting from the original input features, PCA creates new features, which are linear combination of the original ones. Let's look at this image that shows points in a two-dimensional space. As we can see, these two features look very correlated one with the other, as the points lie very close to a line. If we want to reduce the input features from 2 to 1, which choice would we make? If we consider that line and we project all the points onto that line, this will entail a linear transformation of our data. This new feature allows us to replace the two original features by preserving the original information as much as possible. As we will see, the goal of PCA is to produce a new representation that retains the original variance as much as possible. So, how does PCA find out these lines onto which projecting the data? This is obtained by computing the covariance matrix of our dataset. Then, to know which is the most important direction, PCA considers the eigenvector associated with the largest eigenvalue. This is the first principal component, that is, the direction along which there is the largest variance. The values in the eigenvector specify the coefficients of the linear combination of the original input features. The second principal component will be the eigenvector associated with the second largest eigenvalue, and so on for all the other components. Given the properties of eigenvectors, all the new features are orthogonal to each other. Now, how can we choose how many and which principal components to select? First, we must sort the eigenvectors in descending order of eigenvalue. Then, given a threshold on the percentage of the original variance that we want to retain with the new representation, starting from the first principal component, we keep adding new features until the ratio between the sum of the eigenvalues of the selected components and the sum of the eigenvalues of all the components crosses the chosen threshold. In the picture, we see an application of PCAs to a dataset of face images. In the dataset, there are 128 images of faces of size 256 × 128 pixels. In this picture, we see a visual representation of the first 15 principal components, in this case called eigenfaces. And at the top left corner, the reconstruction of a face in this 15-dimensional space. In this way, instead of using more than 30,000 values to represent the intensity of each pixel, we can represent a face with only 15 values. Of course, as shown in this image, the accuracy of the reconstruction grows with the number of eigenfaces considered. Unfortunately, linear combination of the original features are not always able to capture the inherent structure in our data. If we have a dataset with examples distributed as in the picture, we will not be able to identify a principal direction, even if the data clearly occupy a submanifold of the feature space. In this case, we need to resort to dimensionality reduction approaches, able to create new features that are non-linear combination of the original ones, such as locally linear embedding, self-organizing maps, kernel PCA, isomap, and many others. Recently, also deep learning methods have been proposed to perform nonlinear dimensionality reduction. A popular approach is called autoencoders. The idea of autoencoders is to train a deep neural network to learn the identity function. We want the network to be able to reproduce the input correctly. Dimensionality reduction is achieved by using a specific neural network architecture composed of an encoder, a decoder, and in the middle, a bottleneck. The encoder compresses the data to their lower dimensional representation. The bottleneck, also called latent space, stores the lower dimensional representation. The decoder reconstructs our low-dimensional data back to their initial dimension. If such a neural network can accurately reconstruct the input, it means that the features stored in the bottleneck contain the relevant information about our dataset. After training, the decoder is discarded, and the output from the bottleneck is used directly as the reduced dimensionality of the input. Beyond dimensionality reduction, autoencoders are also used for image denoising. In the next lesson, we will see another set of unsupervised learning techniques used to discover relevant patterns in a dataset: association rules.